Now let's investigate a more advanced way of looking at the relationship between angle of incidence and angle of refraction. And this more advanced way was described by a man called Snell in a law which has become called Snell's law. And Snell's law states that sine of theta 1, in other words, sine of the angle of incidence, divided by sine of theta 2, in other words, sine of the angle of refraction, is equal to n2 over n1. What does n2 and what does n1 mean? N is the refractive index of a medium. So we have two media here. We can call it medium 1 and medium 2. We might call it the incident medium and the refracted medium. And each of these media has a certain refractive index. In this particular case, medium 1 is air and its refractive index is 1. And medium 2 is glass and its refractive index is 1,5. What's the meaning of these refractive indices? Refractive index means how much slower light moves through that medium than it does through a vacuum. So you can see for air, the index is 1, meaning that light travels exactly the same speed. Well, not really exactly, but the difference is negligible. It's so little that we can ignore it, we can neglect it. So light travels at the same speed, in effect, as it travels through air, as it travels through a vacuum. And so the comparison of the speeds between traveling through air and a vacuum is equal. It's 1. But light travels slower through glass than it does through a vacuum. How much slower? 1,5 times slower through glass than through a vacuum. That's why N for glass is 1,5. So the bigger the N value, the slower light moves through that material. We say that material is optically denser the bigger that number is, because it's more difficult for light to travel through. So let's go back to Snell's law. So Snell's law says the ratio of the sine of the incident and refracted angles, sine theta 1, which refers to the incident angle, over sine theta 2, which refers to the refracted angle, that ratio is equal to the ratio between the refractive indices of the media, n2 over n1. Notice with the angles, we have 1 at the top, but with the media, we have 1 at the bottom. So just get that right. So the ratio of the sines of the angles is equal to the inverse of the ratio of the refractive indices of the media. Sine theta 1 over sine theta 2 equals n2 over n1. So if we are investigating light traveling from air to glass, n2 over n1 is 1,5 over 1. Why? Because n2, medium 2, is glass with a refractive index of 1,5, and medium 1 is air and its refractive index is 1. 1,5 divided by 1, of course, is 1,5. So the purpose of this investigation we're going to perform now is to verify Snell's law, to check that it's true for light moving from air to glass. But let us put it in this format. How does independent variable affect dependent variable? So what are we going to change between our treatments? What is going to be our independent variable, and how is that going to affect our dependent variable? Now, we've actually already collected the data for this. It's the previous investigation we did. We're just looking at it a little differently. And can you remember that in that previous investigation, the thing that we varied was the angle of incidence, theta 1. But now we're going to look at it a little differently. So what do you think we should write on each of those lines? How does sine theta 1 affect sine theta 2 for light moving from air to glass? And remember that if light moves from air to glass, our two media are 2, glass, 1, air, and N2 is 1,5, N1, 1. So N2 over N1 is 1,5. So remember, we have already collected this data. So I'm putting this data into this table, but giving some space for what we need to be able to look at this a little differently. Remember, we varied the angle of incidence and then we measured the angle of refraction. But now in this this question, we're not asking how does angle of incidence affect angle of refraction, but rather how does sine of angle of incidence affect sine of angle of refraction. So we need columns for sine of each angle. And then of course we know that actually what we're trying to do is to see whether when we divide sine theta 1 by sine theta 2 for each of our readings, are we going to get the same answer as the ratio between glass and air's refractive indices? So that's why we need another column so that we can verify Snell's law. Sine theta 1 over sine theta 2. So you should pause the movie while you work out sine of each of those angles and also work out sine theta 1 over sine theta 2 for each entry. And I hope this is what you found. Can you see that each time you divide sine theta 1 by its sine theta 2, you get 1,5. 0,17 divided by 0,12 equals 1,5. 0,34 divided by 0,23 equals 1,5, and so on. And this 1,5 is a very special number in this case because it happens also to be the ratio between the refractive index of glass and air, the refracted medium and the incident medium. N2 over N1 in this particular case is 1,5 over 1. So here I've plotted the data. All that's missing is for you to determine what is the independent variable, the dependent variable, and how do we write the heading for this graph. Pause the movie until you've done this yourself. Sine of angle of incidence. Now you might have called that rather sine theta 1. It's the same thing. That is our independent variable, goes on the x-axis. And sine of angle of refraction, you might have called it sine theta 2, is our dependent variable. It goes on the y-axis. So our heading is angle showing the effect of sine of angle of incidence. Remember, you could have just said sine theta 1 instead of sine of angle of incidence on sine of angle of refraction, which you could have called sine theta 2 for light moving from air to glass. Now there's something interesting here. Let us work out the gradient for this graph. Now you can take the gradient for any section of the graph, but maybe the easiest is to take for the whole graph, which is what I've done here. So gradient is rise over run. We need the rise, difference between the greatest y reading and the smallest y reading we have, which is 0,66, that's our greatest y reading, minus 0,12, that's our smallest y reading for this particular data, and the difference between that is 0,54. So that's the rise of this graph. The run is how far the graph extends horizontally. So it's the maximum x value that we have in our readings, which is 0,98, minus the minimum x value we have for our readings, which happens to be 0,17. Get the difference between them, you get 0,81. So that's the run. So what is the gradient of this graph? Rise over run, 0,54 over 0,81. And what is the meaning of the gradient? The rise is the change in the y-axis for our minimum to maximum reading, and the meaning of the y-axis is sine theta 2, and the run is the change in the x-axis's readings, sine theta 1. So change in delta sine theta 2 over change in sine theta 1 equals 0,54 divided by 0,81, which equals 0,66 recurring. Let's write it as 0,67. Why did we calculate this? What does it help us with? Let's remember the ratio between the refractive indices of glass and air can be written either as N2 over N1 or as N1 over N2. If we write it as N2 over N1, the answer is 1,5. If we write it as N1 over N2, it's the inverse of 1,5, which is 0,6 recurring. We can write it as 0,67. So we can see that the gradient of this graph gives us the ratio of the refractive indices of the two media that the light is moving between. If we like, we can give it as 1 over gradient, and then we get the answer in the format that we like for Snell's law, which gives us the answer of 1,5 in this case. So let's give our conclusion. The question is, how does sine theta 1 affect sine theta 2 for light moving from air to glass. And we can see from the straight line of the graph that sine theta 2 is directly proportional to sine theta 1. And the gradient of this straight line graph, or rather 1 over the gradient of the straight line graph, is equal to 1,5 for light moving from air to glass, which is the same as the ratio between the refractive index of glass and the refractive index of air. In other words, we have verified Snell's law for light moving from air to glass. We found that indeed sine theta 1 over sine theta 2 did equal n2 over n1, and both in this case were equal to 1,5. Now this was just for air to glass. In another investigation, we'll check whether this works for any two media.